to do. Okay. So, all right. So I'm just kind of making sure I got a feel for where you guys are and everything. So thanks for kind of dealing with that right now. Okay. So I'm just going to share my screen because that's probably going to be easiest. Then we can talk it through. So likely we'll go over Bayes and then naive Bayes classification itself, which uses Bayes theorem, which I think is always a fun one, Bayes theorem and everything. But okay, so let's see here. We're on module 3. Section 28 is basically what we're going to talk about, right, today. We'll mix it in with earlier chapters. I think it was like mod 2, right, with the Bayes theorem and everything like that, in case he's had some head nods. And so I was just kind of getting a feel for where you guys are. You guys have done decision tree. Oh no, you guys done an ensemble methods, right? So that probably meant you did decision trees as well. Is that right?
Yeah. Yes.
Okay, cool. So how are we feeling about like all these machine learning methods, at least like decision trees? Did you guys do k-nearest neighbors yet? K-nens? Yeah. Okay. How are we feeling about these different like methods, ensembles, decision trees, k-nearest neighbors? Thumbs up for like, yeah, it's awesome. I got these down. Side's like, I'm still figuring it out. Thumbs down, like, I don't even know what machine learning algorithm is. Okay, good. So I see some, like, I like this one right here, Miguel, like the kind of like sideways upwards. It's honest because like I kind of get it, but like maybe there's some stuff I'm missing, right? Or like maybe there's some more improvement. I will tell you is that the good thing, like this module in particular, as you guys probably guess, is machine learning, right? A lot of this is basically, the main process is that we have our input data, we have what the expected outputs are, our targets, right? And what we're going to do is essentially say, hey, let's teach an algorithm to figure out how they connect here to here. And, you know, for example, you guys learned k-nearest neighbors, decision trees, ensemble methods, which can be really powerful. And then we'll talk about naive Bayes. These are just basically other algorithms to say, okay, if we know what we're supposed to have to begin with, and we know what we're supposed to end up with, can we make predictions for the future? That's essentially what's going on. So usually, like, people will put linear regression kind of separately from this, but it's kind of like linear regression is like the first machine learning algorithm, except you kind of essentially have to like tell the algorithm exactly what to do, what features to pay attention to. The ideal for these machine learning algorithms is that we can offload us figuring out exactly what features to put in and offload it to the computer for the algorithm to actually figure out what the best thing is. Okay, does that make sense? Like, just kind of frame a little bit like why we're talking about naive Bayes. Different algorithms will have different, you know, like I would say, not abilities, but like they have certain advantages. Especially these earlier ones, for example, like naive Bayes, it's actually a really, really nice one for like classification of documents. So basically, when I say a document, I mean like more of a technical term. Like when you talk about corpus, have you guys heard of corpus yet? No, not so much. So corpus usually is like a collection of writings and stuff like that. So you might have a corpus of different newspaper articles, for example. A document, when we talk about in the NLP space, natural language processing, a document is talking about the sense of like a bunch of words or, you know, like a thing that we're looking at. So a document could be like an article. A document could also be like a tweet. So that's the idea. We say, oh, we're looking at a specific document. So one thing we can use for naive Bayes, we'll kind of talk about this a little bit in a second, is we can use naive Bayes especially really well to say, hey, what, like the classic is this email spam or is it, you know, ham? Is it a good email or is it a bad email? Should we filter this out? And naive Bayes is actually really powerful for this because basically you're like, hey, we'll talk a little bit the things, but we say, what are the words that are being used? And are the words being used in here likely spam or is it likely not spam? And that's what naive Bayes comes from. Okay, cool. All right, so we'll dive right into it. But before we do, I should probably share. So this is where I can basically just keep like, for like whenever I teach study groups, I just keep all of my material in here because honestly, I forget where it is otherwise. So I'm gonna share this repo with you guys because I'll show you guys specifically what we'll chat about today. So I put that in the Zoom chat and I'll make sure to share on the Slack channel as well. But we're actually gonna focus on this probability stats folder. And then here, guess what? Bayesian statistics or Bayesian classification, right? So we'll talk about Bayes theorem and naive Bayes. So these are the two notebooks we'll mostly focus on and stuff like that. Just so if you guys want to reference and stuff like that, you can fork it and whatnot and do all the fun GitHub stuff. Okay, cool. All right, so let's get right into this guy. You guys still see my screen, right? So Bayesian classification. All right, so we're gonna open up this notebook. I'm gonna close this guy since we don't need to open. And we're gonna fold this guy All right, so you guys haven't talked too much about Bayes' theorem itself, right? Right, okay. So I'm just gonna make sure I have everything all set and ready for us. Okay, so we're gonna go through a whole bunch of stuff. Forgive me if I kind of talk a little fast. So at any point, if you like I'm not being clear or you want me to repeat something or you're like, hey, I have a question about this, feel free to interrupt me. Like, don't feel bad at all. I actually encourage it, all right? So Thomas Bayes, which is what Bayes' theorem is named after. It's actually, like I said, the badass of probability, which is like if you ask them, like, hey, like Bayes' theorem, and be like, yeah, Bayes' theorem. Like that's kind of the reaction. It is it's such a powerful tool that when you talk about it, it's just one of those amazing. It's like, oh, like it's kind of like if you guys ever do physics, like F equals ma. It's like earth shattering. Like, oh, we can actually describe the acceleration of like masses with the forces. It's kind of like that equivalent of like, whoa, like this is like pretty like big stuff. And it seems very like intuitive, or I don't know, intuitive, but like very obvious once you're told, but it's so powerful as a tool. And that's where naive Bayes classification is going to be based off of. Okay. So what do we mean by Bayesians, right? So this is where, to be honest, I would have assigned you guys a little bit of homework beforehand. It's not really that homework, but it's a great little blog here. And I'm going to go ahead and share this in the chat as well. So you guys can take a look at it later, but we'll look at it right now. Basically, like that's kind of a cool idea, is that they're using Bayes' theorem to figure out, if you guys are Star Wars fans, in the first movie, Han Solo is flying through like the asteroid belt or asteroid field, I should say. And C-3PO basically says like, sir, the possibility of successfully navigating asteroid fields is approximately 3,720 to 1, right? And he says, never tell me the odds. And so this blog actually does a really fun job of actually like literally going through the odds and saying, hey, how likely is Han Solo going to actually get through this? And I won't go through the full details, but it's a great read. It's all like pretty like mathematically sound. And it's based around Bayes' theorem. And so the main idea here is that with Bayes' theorem is that you start off with something called a prior. And basically what that means is that it's the knowledge of what you already think is true. And kind of summarizing this whole article basically is that C-3PO reasoning is not necessarily wrong, but one thing he didn't take a factor in there is that Han is really a really good pilot. Like basically he's a badass pilot. And so like he didn't factor that in, is that the likelihood of him actually passing through is different from like the average rate of success for any given pilot going through an asteroid field. It's kind of a fun read and kind of shows a little bit of like what this looks like. My favorite thing about this though is that he actually goes through saying like, well, what do we mean by like good pilot? And he kind of gives, some kind of like values like, well, what we think it is, and versus like what C-3PO is saying, and saying what's the probability that we know as the audience, like he's a good pilot, but also asteroid fields are really hard to navigate through, as the audience being like, oh, it's suspenseful enough where it's like not certain, but it's like a more certain than C-3PO, but still enough to be like put you on suspense. So anyway, I think it ended up being like about 0.7, 75% chance survival. Anyway, a good read. I think it's kind of shows a little bit of like how you can apply this kind of stuff. Like obviously not to really movies, but like the idea of like when we have a prior knowledge, we update our prior belief, right, with Bayes' theorem to get our posterior, basically saying, now what do we believe? So the classic of this is something along the lines of like, if you know the sun rises every single day, like it's been rising every single day, you're like, oh, I have a very strong prior belief that the sun's going to rise in the east, every single day. But like there's a probability that it might not, right? And you would assign basically, well, let me update my belief based on what happens next. So let's say for some reason the sun doesn't rise the next day, right? You would update your belief to say, well, I was really certain, but now something changed in that I have to update my probability of the sun rising up every day. That makes sense? Like, it's not a silly example, but that's kind of the idea of Bayes' theorem. So it seems very obvious, I think, when you say it out loud. It's like, yeah, you have a belief and then you update it, but that's not usually how we think of probability. Usually we think of it much more in the frequentist, which we'll talk about. Some other examples of this is, everyone always complains to me about saying coins and probability, but like, it just makes a lot of sense a lot of times. But like every time I flip this coin, it lands on heads. So next time I flip it, it'll likely land on heads again. This might be actually kind of false, but think about like if you flip the coin like 5 times and you see heads every single time, you're like, whoa, like maybe maybe this coin is actually like, biased towards heads, right? Maybe it's actually like a trick coin, right? So I might have a prior belief based on my knowledge of this trick coin, like, hey, that might actually be like it's not 50-50. And then I would update it. And so if I flip the coin a 6th time and I find it's head or tails, I'd be like, oh, like I have to update my belief, say, oh, it's probably not as likely as I thought. However, if you flip the coin like 1,000 times and it landed on heads every single time, like you can say technically you got really lucky, but like, I think instinctively, you know, like there's something up, like there's probably something going on here. So you have a prior belief of saying, well, it's very, very likely that the next flip, the 1001, you know, flip is going to be a heads again. Does that make sense? So it's very different from what we will talk about like frequentist. When we talk about frequentist, it basically says, oh, we need to like basically do the full like test out, like flip a coin very long before we can tell a probability. Where Bayes' theorem kind of says, hey, if you know something else about this information, like for example, if you know like someone goes to you like, hey, we're gonna flip a coin for heads and tails, and like they're kind of laughing a little bit. It's like, you know, like, oh, like you want tails? Like I think it's heads, and they're kind of like giving a little smirk. You're like, I'm going to have a slightly higher probability that maybe it's going to be biased towards heads. And that's the kind of idea what we can do with Bayes' theorem. Okay. Does that make sense to people? Okay. And the big thing about Bayes' theorem is that it quantizes that. It says, what do we mean when we say we update, you know, when we see something new happen, or our prior belief, our prior, you know, knowledge. Okay. Cool. So I'll just kind of quickly go frequentists. So like there's kind of like the Bayesians versus the frequentists, you know, like it's not a real like real factions and like war whatever and all that stuff, but basically it's kind of like different ways of thinking of probability. So interpretation from a frequentist is much more like the limit of frequency after many, many trials, where Bayes actually assigns a probability that the hypothesis that they're looking at is true or not. So frequentist kind of is much more of like, I think very like straightforward, like okay, like we have to measure the probability by flipping it many, many times. Where Bayesian says, well, we can assign a probability of a chance of it happening before we actually do the experiment. Does that make sense? Okay, cool. It's a little subtle, but it makes a difference. So just know that sometimes like it makes sense to actually think of it in a frequentist mindset, and sometimes it thinks like it makes more sense to think of like in a Bayesian mindset, where like, hey, we already have some prior knowledge, let's update that belief. Okay, let's hear. Yeah, I'm going to kind of skip this over, but you can kind of think of it like one that would make sense. The big thing when you do Bayesian is that if you already have some prior knowledge or talk to other experts that have some knowledge of what this like, you know, probability should be ahead of time. But note that that can also change, right? Maybe the experts are wrong. Maybe there's new data that wasn't accounted for. Those are the kind of things that could update your probability, where this can actually make a lot of sense. Okay, cool. Sound pretty good? Any questions so far? Just that kind of concept? Cool. I know it's like you're just like, where's all this code? Like, you know, let me see this code stuff. But it helps a little bit to kind of think about what's going on here. So Bayes' theorem. So really fun fact, really quickly, is that Bayes never actually published or even wrote the theorem down that we're going to see. He actually felt it was so obvious that like it's like, oh, I don't need to write this down. This is obvious. And it wasn't actually until like his friend Richard Price, when actually Thomas Bayes actually passed away, went through basically all of his papers and found that like hey, like this is Bayes, or essentially what they called Bayes' theorems. Like, hey, like there's this concept in here, and it was actually him who wrote down the theorem describing what Bayes was talking about. And so I thought it was kind of interesting because basically I was like, oh, this is really obvious. I don't even want to talk about this, and we actually use it quite frequently. So really quickly, I guess I can show you like the power of what this looks like. And I'm going to go this really quickly. So like, forgive me if it kind of confuses you a bit, but here's a little YouTube video that I think really does a great job of explaining it. Plus, they actually do this little thought experiment in actually like Thomas Bayes' old house, which is kind of fun. Number 5 if anyone watches any YouTube stuff. But anyway, basically, Bayes thought of this scenario like where he's sitting like where I am, and there's a table behind him. And the idea is that he tosses a ball into the table, which will land randomly somewhere on that table. And then it's going to land somewhere, and then he has an assistant say, okay, that's where the ball landed. And then Thomas would throw the ball up again, and it would land somewhere on the table, you know, in relation to that first ball. Okay, so when he first throws that ball, he doesn't know where it's going to land. It could be randomly anywhere on that table. So if I just drew a really quick picture of this, like this guy right here, and let's say Thomas is right here, my great drawings, and let's say the ball lands right here. Okay, well then if we have the next sequential ball, right? Like it could have landed anywhere. He throws the ball and it lands randomly again, like over here. Okay, and then he just says, hey, like assistant, like where is the ball in relation to the original ball? And he goes, oh, well, it's off to, and we're going to use it from this perspective. Like, oh, the original ball is, or the second ball you threw is to the right of this ball, of the first ball, and downward from the first ball. So he kind of takes things like, okay, it was off to the right, it's off to, you know, kind of downward, and then he throws another ball, right, which is going to land like right over here. Okay, and then he says, oh, same thing. It's going to be downward and off to the right. He goes, oh, okay. Like when you start seeing that, and assuming it's thrown randomly, you can say, oh, my first ball probably is in this like first quadrant, right? It's like, oh, in order for balls to kind of be downward and upward, and basically as you get more and more balls, he does it over and over and over again, he can get a good idea, assuming, you know, sometimes the ball will land over here and be, oh, up to the right, but most of the balls are going to be over here, where they're going to either be at the very least left, right, or sorry, right of the original ball or down to the original ball. So he can get a good idea of like where this original ball was. And that's the idea of what Bayes' theorem is using. Okay, does that make sense to people? Like that kind of analogy going through? Cool, thumbs up if that makes sense. So I can go, okay, cool. So you can see a little bit like what the power is here. So, okay, cool. Like that's the idea. How do we actually represent this math? So we actually get some math in here and actually write this stuff down. So here is the amazing Bayes' theorem. Woo-hoo. All right. So I don't know. I don't know. Depending on how you read this, it's like, oh, this is amazing. It's not amazing. So it kind of helps a little bit. Oh, my stuff's like all garbled up. Helps to kind of break this down. And there's different ways we can think about this, but I particularly like this formulation right here. Usually you'll see it written like in this form. Okay. And the way we read this, do you guys know how to read this when we say probability of, with this guy might kind of help. It's the probability of A such that B, right? So it's the probability of A happening given that B happened. Does that make sense? So it's like the probability of it being sunny, given that we know it's raining outside. It's like, oh, there's probably a smaller chance of it being sunny outside when it's raining. Okay, so that's essentially what we're reading here. And so we have different parts. So the first part is we have the prior, so P of A. So the probability of A happening. And that's kind of like, this is the thing that we're usually wanting to kind of figure out, right? It's like, oh, wait, what is the actual probability of A happening? I'm sorry, this is kind of like, we have an idea of this, of like the probability of A happening. Think of it like the coin flips. Like, oh, I think it like the chances of it being a 50% heads or tails is like 0.3. Okay. Then we have the posterior, which is AB. That's the thing that we're actually updating. So we'll take A right here, probability of A. We'll update it, right, to get the posterior. And this is kind of like our new updated version. So if we're flipping a coin, for example, our P of A of our first coin flip and say, hey, the probability of it being 50-50, right, is probably like, oh, like near 100%, like 0.9999, right? And then we flip it and it's heads, 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 heads. We're going to update our beliefs like, seems more likely like that maybe I was wrong originally. So our probability of A such that B is happening, meaning that B, I get heads again and again and again and again. That's how we're going to update our belief. Does that make sense? Okay. And then we have this last part, the likelihood. And the likelihood basically is what you're actually observing. So it's like, oh, the probability of B happening, essentially. It's not quite written this way. Like we can talk about like likelihood. Likelihood actually means like something very specific mathematically. But essentially you can think of like, what is the thing we're observing? And then we use the information that we believed already, and then what we observed to get our new posterior, our new updated belief. Okay, does that make sense? Kind of breaking down that math? Cool. All right, sound pretty good? Thumbs up, thumbs down? How are we feeling? Okay, cool. All right, so let's see, I kind of feel like, okay, so we're gonna have a little example of this. And this is the classic Bayes example, which is basically you test positive for a disease, okay? Which, especially during COVID's time and pandemic stuff, is kind of relevant to us. Like if you get a positive test, like what does that mean, right? Because we also know that tests aren't necessarily always super accurate, right? But like how accurate does this have to be? And then like if it is super accurate, what's likely gonna happen? So let's see here. So kind of going through, I just go open this guy up here, is that we're just going to pretend we test for positive for a rare disease. So not, in this case, probably not COVID because COVID's not super rare, but like some disease or whatever, like, hey, like the doctor's like, you know, we should take this test, whatever. And you gave your test like, oh, you tested positive. What does that mean? Now, most people's reaction, including myself, if I got this, would probably be like, oh shoot, like, do I have this super rare disease? Like I tested positive for it. Like, what does that mean? And we're gonna go through here and kind of see like, well, okay, we can actually calculate about like how likely we think we actually have this disease. And so we're gonna pretend that basically, let's see here, I have these little notes here, is that the probability of actually having the disease, so like, because like the overall population is like, what's that, let's see here, that's 1%, 0.01%. So very few people in the world actually have this disease, right? So it's like very relatively low chance of, like not very common, but I do test positive. Okay, so we can actually break this down. So, okay, like then you ask the doctor, like, hey, like when I test positive for this, what does actually that mean? The doctor like, oh, you're a data scientist? I can give you a bunch of numbers because every doctor loves to give numbers, right? I don't know. So we can assume the disease is really rare. Only 0.1% of the population actually has it, right? So relatively rare. It's not something that everyone has. So it's like, you know, not common. So it's a good thing that they caught this disease, right? The test is 99% accurate. And this is where it's subtle, where when I say 99% accurate, there's actually two different probabilities. Basically, it's that the accuracy that you are predicted, what's it called? If you, if you are positive, are they likely to catch, like, how accurate is that? It's like, oh, it's 99% of the time, it'll say that you're positive when you are positive, right? The other 1%, it'll be like negative, right? Even though you were actually positive. Does that make sense so far? There's a secondary one, which could be like, if you're actually negative, what's the probability of the test being accurate? So in that case, it could be something along the lines of like, okay, you are negative, and 99% of the time, it'll say you're negative, but 1% of the time, you'll get a false positive. Does that make sense? Those numbers don't have to be the same. Just know that, right? And that kind of makes sense. It's like, for example, let's say we had a special test that could detect if your arm was cut off, right? And your arm is cut off, right? And what? Sorry, I lost track of like what I was even trying to get at. I think I got distracted by the arm. But it's that if you like, let's say for example, oh man, I'm trying to think of a good thing to do here. But basically think of like certain factors might be like really obvious. Say, oh yes, you definitely have the disease. Versus like things like, oh, you might have the disease, you might not have the disease. So maybe if you're negative, it's like only 50% accurate. Does that make sense? Like how you can have a difference in testing? Okay. They're having these issues with the COVID testing, by the way. Like when you talk about antibody testing and stuff like that, it's like, oh, what does it mean by accuracy? So we'll just pretend though, just for simplicity, is that 99% of the time, it's able to say whether you're sick or not. So if you're sick, 90% of the time it says you are tested positive. And then if you're not sick, 90% of the time it'll say you're not, like you're negative. Okay, just to make things simple for us. Okay, so kind of using what we have here, we can kind of go say, what is this formula? Like, how do we use this formula based on what we have? Now, since we're kind of going to also go through naive Bayes classification, I'm going to kind of just speed up through this versus like you guys going through the answer. But think about like what are different parts that would actually fill into this Bayes theorem to actually fill it out. So we'll kind of go. I'll just kind of write it out here. So we have Bayes theorem, and note that we have the probability of A, right? Let's see if I can kind of make this a little bit easier for us to see. So the probability of A, right, given B. So the probability of us being sick, given that we tested positive, because remember, we did test positive, so we actually want to know, okay, what's the probability of me actually being sick now that I tested positive? Well, that's going to be equal to the probability of me being positive, given that I'm sick, or sorry, test positive, given that I'm sick. So note that's a little subtle difference than this guy right here. This is saying more saying, okay, what's the probability of me actually testing positive if I am in fact sick, right? And then what's the probability of us being sick divided by the probability of me testing positive. Okay, does that make sense? Okay, so that's kind of how we fill this out. And that's essentially this A-B part, right? And then say, okay, we can simplify this a little bit by knowing the probability of each case. So what's the probability of me testing positive? It's like, well, there's a few cases, right? Well, I guess two. I could be sick and test positive, or I can be not sick and test positive, right? So we have to add up those two probabilities. So the probability of me being sick, okay, and testing positive is the probability of me being sick, so I have to be sick first, right? Times the probability of me testing positive such that I'm sick, which this probability here is what you said is 99%. The test is 99% accurate for those things. So 99% of the time, if I am sick, I will test positive 99% of the time. Make sense? Okay. Then plus the probability of me not being sick, which is pretty high, right? It's like very likely that I'm not sick, right? Because it's a very rare disease. And then the probability of me testing positive such that I'm not sick, right? Which is not 99% now, right? It's 0.1% or 0.01%. No, sorry, just 1%. So this is basically saying like, I am not sick, but I still test positive, right? That's the other example here. And that's where we're like, okay, we're getting this, it's too many P's, probability of being positive, okay? So we're just gonna basically fill this into here, substitution, back in like, think back into like algebra when you're back in school, like grade school and stuff like that. And we just fill this out right here. So note that we basically, at this point, we have everything we need, right? We know the probability of me being sick. right? Just the general population. We know it's a rare disease. We know how good the test is, the chances of me being tested positive when I am sick. And we also know the probability of us not being sick because it's just the inverse of probability of sick. And then the probability of being positive such that I'm not sick, right? Which we know is 1%. Okay, does that make sense right now? Okay, so with all this information, we can actually figure out now what's the probability of me being sick such that I'm positive. So before we actually run this through, right? We'll go through real quick. It's like, okay, we can actually run this in code. It's like, hey, code, right? Okay, so the probability of being sick is 0.01 or 0.0001, right? Probability of not sick is 1 minus that. Okay, simple enough. Okay, probability of me being sick on the tests, or testing positive such that I'm sick is 99%. Probability of positive that I'm not sick, it's just that 1% of the time, right? So I get this number. Okay, everyone follow me so far? Yeah. Okay, so then this is the full solution right here. Oh, sorry, not full solution. This is this part right here, is this guy. The probability of me testing positive are going to situations where I'm sick and not sick, right? So relatively small, or relatively small for if I'm not sick, this probability. Okay, so okay, we got all these different parts, ready to find it. And now what we're going to do is, okay, we're just going to fill this in. What's our prior? Our prior is a probability of being sick. Our likelihood is a probability of positive, testing positive such that I'm sick, divided by how many times we actually test positive. Okay, because you really want to see if we're actually sick. So that's where our likelihood's coming from. Okay, and then okay, I'm actually going to find a little handy function just to build up suspense. Is actually find the posterior, which is basically just saying, hey, multiply the prior times the likelihood. You see in those terms, it's a lot easier to understand, like, oh, that's where this formula is coming from. And then I find the results. So before I actually run this, right, what do we think? If I test positive for this rare disease that's only in 0.01% of the population, it's a 99% accurate test. What are my, just kind of give me an idea, what do you think the chances of me actually being sick are, assuming I tested positive? I'd say there are no wrong answers because there's obviously a right answer, but what's your gut feeling? Like when I say this, oh, you tested positive for a rare disease that's 99% accurate. What do you guys feel?
It's very high.
So very high chance that you are sick, right?
Yeah.
Okay. Thumbs up if you agree with that. Thumbs down if you're like, I think I'm in the opposite direction. Thumbs up, yeah, I think that's about right. Okay, I saw the thumbs down. So Sam, tell me why thumbs down.
I think it's going to be a low percentage because it's such a low probability that you actually have it.
Okay, so going the opposite direction, be like, hey, the test is super accurate, but it's unlikely for me to have this disease. Okay, good. So those are two possibilities. I think most people are kind of either one of the spectrum. Most people are oh, it's still uncertain. I think most people are kind of oh, it's one of those two situations. So let's find out, right, based on base. And it is 0.98% chance of actually being sick. So it's actually really unlikely to be sick. And this is a clear thing. Basically, kind of what Sam was saying is that this probability right here really wins out. Essentially, hey, you are likely not sick, to begin with, essentially. So you are likely not sick, and then you can see in the, let's see here, the probability of me being sick right here, right? This is a really low number. So that essentially ends up winning out. So you can see less than 1% chance that you actually are sick, even with a 99% chance or 99% accurate test for both ways and everything like that, for negatives and positives. So I think that's kind of counterintuitive for a lot of people. At least it's counterintuitive. I know this, and even then I have to kind of convince myself, that's right. Okay, it's very unlikely for me to have this. And so that's kind of the power of what Bayes' theorem has here. Okay. And again, interpretation making sense. Yeah, I think that makes sense, right? Is that basically hey, we are very, very unlikely to be sick. So it's probably, it's more likely for us to have a false negative because we're so unlikely to actually be sick to begin with. Okay, makes sense? Cool. All right, so round two, right? So, okay, you get your test and the doctor says, hey, chill out, we're gonna do a secondary test, all right? And so we're gonna do a different test. This test has the same accuracy, but it's a different kind of thing. It's independent from each other. We're not just taking the same test again, right? And in this case, I test positive again for this disease, for this rare disease. Okay, we can actually update this code now, right? So the simple code is okay, our prior now is now the probability that you're sick, right? Which is from this right here. Basically, we already know what our probability is, so we're using that as our prior, and now we're updating it by saying, hey, we tested positive again. What does this mean? Okay, And so using that, and like, remember, nothing else changed, right? The only thing is really is like, you know that we tested positive once, okay? So if I do this now, what do you think the probability is now? Like, do we think like, remember it was less than 1% chance that we were sick for this rare disease, okay, after testing positive once. If we test positive again, do we think it's just as rare? Do we think it's like a very low chance? Do we think it's a high chance now? Do we think it's like a medium chance? What are we thinking? At least you're like, it's kind of confusing because it's like, oh, you have Bayes, but you also have like your instinct, your gut feeling. So like, what do you guys feel? You guys are hesitant now that I've tricked you all for the first time, right? So. Okay, I see Miguel going kind of like up to, Miguel, do you mean like really high up or like, oh, like, I don't know. Throw a number.
I'm just gonna say really high up. I'm gonna
Really
roll
high
the
up?
dice. Yeah.
Okay. So you think like now that we tested, like it was only 1%, less than 1% chance that we were positive, right? And now we tested positive again. You think it's gonna go up to like what? Like when you say really high up, you mean like 70%, 80%, 90%?
Like 75.
75. So like still not certain, right? But like
high enough,
higher,
yeah.
like significantly higher. Okay.
Yeah.
Okay. Thumbs up if you agree. Thumbs down. Abstaining. Okay. Yeah. So let's find out, right? So it's suspense building. 96% chance, which I think like when you think about this too, like Miguel's like, yes, but like even then, it's like you think about that's really certain, right? Like we took a test with the same kind of accuracy, and I think this is where like it's hard to like wrap Bayes' theorem around your head for a second, because you're like, wait, but it didn't increase very much. But then if you think about this from like your gut feeling too, is also kind of confirms a little bit like how you feel. It's like, hey, I tested positive once, I tested positive again on a different test. Seems likely that I'd have the disease, right? It seems unlikely that would still be there. No, that's still not 99%. It's still at 96%, but that's where like, oh, it's even more certain now. And so that's the kind of idea where we can use Bayes, and that's the idea where we can take a prior belief and actually feed it back in and update our belief. Okay.
What would be the chance if you took a third test now?
Yeah, good. We can try that, right? So we can actually change this now, right? So now that the probability of us being, let's just do prior. You can see now it's 96%, right? Let's say we have a third test, a third independent test, and you test positive, right? What does that look like? So I'm going to do after 3 tests just so I don't mess up if I want to change this. So first of all, we should probably say its go up's higher, right? But it's probably not like significantly higher. In this case, oh, my math's wrong here. Oh, it's probably because of this guy right here. But yes, it should be much higher. I think my math is messed up on this case. I have to think about what I did wrong. But it would go increase higher and higher. It would never get 100%. It would get up to like 99%, 99.99%. It get higher and higher and higher. Okay. Oh, you know what it is? This is why. Oh, wait, maybe not. I have to see what I did wrong here. There's some code issue. That's going to mess with me. What was my likelihood? But yes, it should increase higher. Note that if you tested negative for your third test, it still would be, oh, this is why. Likelihood should be divided by. There we go. So 94% chance. I think it's technically lower. Is that right? Double check that. Anyway, it should increase higher and higher as you get more and more positive tests, which makes sense. If you had a negative in there, it would kind of lower it down, but you still would have that prior belief really strong, like a 96%. So it would only drop it down like a slower amount. Okay. Cool. Any questions? Sound pretty good? Okay, we're all good Bayesians now. We understand? All right, cool. So you're like, that's cool. Bayes' theorem, awesome. Let's talk about how we can use this for classification now, right? So let me go ahead and get to naive Bayes classification. Sorry, I'm kind of thrown off right now. There we go. Okay, so Bayesian classifier. So as you can probably guess, we actually are using Bayes' theorem to help us do classification. And so this is where like usually if we introduce this to begin with, I talk about classification. So note that with supervised learning, right, which is basically you know the beginning inputs, right? You know what the features are, and then you kind of have the results, and you train based on saying, hey, okay, this is the inputs, this is the answer, the target, right? Figure out how to do this. This is supervised learning. There's classification. What's the other type of supervised learning we can do? It's Classification, which tells us like yes or no.
Regression.
Okay. Regression, right? Which is basically a continuous value, right? It's like, oh, like linear regression. Versus logistic regression, right? Logistic is basically saying a yes or no answer, right? So classifying. So note that base theorem we're talking about linear, or sorry, in this case we're talking about classification. Okay. So we'll just kind of skip over this. But one thing to kind of note that when we do classification, it doesn't necessarily refer to the degree of like if our classification is correct, but just saying if they are classified as this. There are some algorithms in the ways you can kind of tease out information like feature importance, things like that, that can tell you how certain you think this classification is, but classification by itself doesn't rely on that necessarily. Okay? Just kind of keep that in mind, right? So naive Bayes, so spam, all right? So this is the classic example, is basically we use naive Bayes, and the reason why it's called naive Bayes, we'll talk about this, basically we're gonna assume some things, and it turns out this naive assumption is actually good enough to get us good results. But the classic example is like we have an email come in, and we wanna know, based on what words are written, if it's spam or not. Now, as you might guess, this can be a really tough problem if you're, like, if you think about like, how do you identify spam? So I kind of mentioned like you could look for certain words, right? And maybe the order matters and stuff like this, right? For example, it's like, hey, like I don't know, like I'm trying to think of a good example of this, but like let's say a certain word and there's like cache. Cache can be like something like, hey, like that's not usually a typical email. That's usually found in a lot of spam. But maybe someone, for example, is like, hey, I want to pay you back for your cache that you lent me yesterday or whatever, like in an email. In that case, it's like, oh, like it is in that case. And maybe if you knew more information about that email, or like you were careful about saying, oh, the order of the words, we could potentially like figure it out, right? Naive Bayes basically skips over that. Says we don't even care. All we're going to care about is basically what words are in there and how frequently they occur. Okay, and then we actually can use Bayes theorem, and it turns out it's actually pretty powerful. In fact, if you guys have been using email since like the 90s, spam has gone down quite a bit, but it's not because there's less spam. Most of it's because we got better detection systems. And one of those systems that was a big deal was when we had naive Bayes classification actually was used for email classification for spam. There's more advanced methods we can do now, but it's still like a really powerful one. Okay, so this is how we're going to kind of set up our naive Bayes, right? So what we're going to do, we're going to look at spam and not spam, we call them ham emails, right? We want to identify the words that suggest classification. So the idea there is that we want to identify what words make spam spam, okay? Like what spam emails have very similar patterns, essentially, okay? And then we're going to determine probability that words occur in each class, right? So we're basically saying, hey, like for each spam, maybe cache is used, 10% of the time, but like for not, like for ham emails, we have like, oh, it's only used like 1% of the time, right? So there's a difference in that probability and stuff like that. And then what we're going to do basically is we're going to use that information to classify new emails as spam or ham based on what's the frequency that they're actually using these words in there, based on what we've seen for spam and what we've seen for ham. So again, this is supervised learning, so we have to know what is ham and spam to begin with, right? But once we have examples of this, we can actually include this in here. Okay. Make sense? Okay. So some reasons like why this is really useful. It's like, hey, we can just keep updating our email, or a way we detect email, right? So we can add new words in there as we get more and more, like a larger corpus, right? So many, many documents, okay? As our corpus grows, we can basically include that now as updating our frequency and stuff like this. It's relatively simple. I just have to look at what the words are. I don't have to worry about the order. I just have to say how often they occur. And we can expand this to multiple words. So if we were looking at just cache, we look at just cache, but then we could also say, hey, what if you use cache and, free and, I don't know, Nigerian prince or whatever, right? Like, it's like, oh, like these words in conjunction all together, that's probably spam. Like that's kind of the idea we can do. We can expand it really easily with naive Bayes. Okay. Cool. Any questions so far? Sound pretty good? All right. So this is a good thing. Like I like to say is that I'm going to go through this more conceptually. So like note that in reality, if you're going to do naive Bayes with sklearn, like scikit-learn, you don't have to like code this by hand, right? A lot of this would actually basically say, hey, we could just use the naive Bayes machine learning model, just like you would use random forests or whatever else you would do in sklearn. Okay. But this is why we're kind of going through this, get an idea of like how this is working, so we can understand when it fails and when, ways you can improve it. So the naive assumption. So I mentioned this naive Bayes, and naive basically, hey, like this isn't quite true, but we're going to just pretend it's true. So basically, we're saying that the probability of A and B, so probability of A and B, you guys have seen this notation before? Yeah? Like this little upside down U. This is the mathematical notation, just as you know for set theory. Basically, the probability of A and B is going to equal the probability of A times the probability of B, which you think about that, that isn't really true, right? Like that has to be not true. Because like we know, for example, if I said, you know, cash in Nigerian prince, those words are probably not independent from each other, right? Like they're probably related in some form, but we're just going to assume with this naive assumption, say, okay, the word cash and Nigerian prince or whatever else phrase we're using are likely are actually independent from each other. And it's not quite true, but it's close enough that actually does a really good job. And so we'll kind of see where this kind of plays in there. Just kind of know that's a little difference. Okay, so good. Let me just fold this up because this is, I want to show little by little. There we go. Okay, so all right, now we can actually do this part. So the formula, right? So now this is just Bayes' theorem, right? And we can read this through. It helps a little bit to kind of read this notation. Is the probability of spam, or sorry, the probability that it is spam such that the word cash is in the email, okay? Okay, so we're trying to figure out what this probability of it being spam. And we can use this by saying, hey, what's the probability of spam? So what's the probability of it just being spam, like without knowing any other information? The probability of actually using the word cash in the document, okay? So that could be it's spam or not spam, right? And then the probability of it's cache such that it is spam, okay? So we're combining all these things together just like we did with the diseases, right? To see, hey, like what is the probability of that this email with the word cache in it is in fact spam, okay? Cool. So kind of, it's useful to think about like, how would we actually find these things? So like, how would we find the probability of it being cache? Like, or the probability of cache? What would that look like?
Go through all the documents and count how many have cache in them.
Yeah, so we had to go through all the documents, right? And just basically saying, how many times is cache used? Now note that this probability is probably very, very small if you count all the words. In general, when you do NLP, natural language processing stuff, if you guys don't know what the abbreviation, usually we'll remove very common words. For example, does the word the really matter in classifying spam and ham? Like, no, like no one cares. So we'll kind of remove those parts and then we'll do some other processing too. But in general, it's like, oh, we just look at all the words and say, how frequently does the word cache occur in this email, right? And note that these probabilities are really, really small. 2% of, if you imagine emails containing 2% of the time cache in it, that would be like a really annoying email set. Like you would never probably want to read emails ever again. But just kind of for the sake of simplicity, we're using 2%, okay? So we have this guy. All right, so what about spam? How would you find the probability of it being, spam? How would we calculate that?
So the probability of cache, is that 2% of all the words in all the documents or 2% of the documents contain cache?
2% of all the words in the documents use the word cache in it. Okay. Or sorry, have 2% of all words are cache. Does that make sense? Yeah.
Yeah.
Cool. Yeah, good. Thank you for clarifying that too. And then so probability of it being spam, that's just simply just saying, hey, how much spam do we have? Like, so this is our prior knowledge. This is our prior, right? It's like, okay, like if an email comes in, maybe 10% of all emails are spam, okay? It's kind of a sad thing, but let's just pretend that's true, right? Is that 10% of all emails are spam. And we can do this because we have supervised learning, right? We basically know what's already spam and what's ham, okay? All right, and so what does it mean when we say the probability of cache such that it's spam? We're basically saying, hey, what's the probability of it being, like how frequently is cache used in a spam email? Does that make sense? So if we look at a spam email, how often is cache actually contained within it, okay? And so we can use this guy right here. Okay, so like this is like you go literally in like your spam emails and basically count how frequently those spam emails contain the word cache. Okay, cool. And that's part of the reason why we have to say the probability of it using the word cache across all emails, because we have to see, like, we have to balance that out essentially, and that's where our likelihood comes in. Okay, so then we can just use our formula right here, which we already have it written out, and we say the probability of, say, if you get an email that has the word cache in it based on these probabilities, likelihood is a 60% chance that email is spam. Okay, which I think that makes sense, right? If you see these probabilities like, hey, 2% of all the time cache is being used in it, probably of spam is 10%, but then like probably of it having the word cache is a spam email is relatively high. You'd expect it to be relatively high too, right? Okay. Cool. Note that this guy right here, the probability of cache given it's not spam is not 12%, right? Or even in this case, 88%. It's a different percentage based on whatever the ham is. Okay, cool. All right, so that's kind of the basic idea. Now, if we wanted to use multiple words, this is when it kind of gets a little like ooh, there's a lot of little symbols and stuff like this, but it's actually not that bad. So the probability of it of having spam using the words like by, cache, and all that stuff. So this is where we actually use the naive assumption. So this is proportional. That's what that symbol means. It's proportional to some number multiplied by this thing. The probability of having the words by and cache such that it's spam times the probability of it being spam. Okay. But what's nice is that because we know this guy right here, because of independence, we can just basically say, hey, the probability of it being by in cache, given that it's spam, it's just simply going to be the probability of by such that it's spam and the probability of cache, given that it's spam. So we can actually keep those separately. In fact, we could keep like a database of saying, hey, like if we really wanted it this way, we can keep the probability of saying how often is by used in the spam emails, how often is cache used in the spam emails. Okay. So that's where our naive assumption. And note that we can expand this out bigger and bigger and bigger, you know, depending how many words we want to include. Okay. But the main idea is that we use multiple words. If we didn't use like the naive assumption, note that would be a huge amount of work, right? Like that would be like trying to figure out this exact probability, because that's why I put proportional, because I'm like, I don't know exactly what it is, but it's gonna be close enough. So that's why we're kind of using a modified Bayes theorem in a lot of ways. Okay, cool. Aaron, get me on that? Like, does that make sense to people? Okay, I see some nods. All right. So now what we're basically going to do, this guy right here, this beast of a thing, basically is trying to figure out this probability of spam such as cache. This is going to just fill out the Bayes theorem itself, right? And so we have the top part, probability of by such that it's spam, times the probability of cache such that it's spam. That's what this came in right here, or sorry, this one right here, times the full probability of it being spam. We saw this before. And then this right here is basically just saying, okay, this is for every word that we use, how often this is actually used for using that it is, given that it's spam, right? And then also note that what's the probability of it happening given that it's actually ham, okay? Because it could be in ham or spam in either way, okay? Makes sense? And so then we could actually use this information, combine this together. If we had the probability of spam, probability of cache, combine this together and we get a probability then. As you can probably see right here is that if we had, let's say cache was already what we already used up here, okay, we would have a higher probability probably if by is a more common word within spam. And what's kind of nice about this is that we can actually take this information and say, oh, it's likely spam, and say, you know, identify this. And then as we expand with more and more words, we can actually use that to help classify. Note that for these kind of cases, is you might have a multi-class. So in this case, we're just saying spam or not spam. But in other classifications, we might have like, you know, class A, class B, class C, class D, class E. One typical thing we can use, like for example, is sentiment analysis. Are you guys familiar, heard that term, sentiment analysis? So later on in the modules, you guys learn about natural language processing. And one of the things you can do is something called sentiment analysis. Basically it says, what is the sentiment of this document? Is it a positive? Is it negative? Is it neutral? Those are usually the typical classifications. And so you can think about how this can be really useful for like a review. Like let's say you have an Amazon review on some product. It's like, oh, is it a positive review, negative review, or neutral review? And the idea there is like, instead of going into every single specific detail, like, you know, how the words connect to each other, you can say, well, what words are commonly used? And you can basically use that now to classify, oh, is it positive, negative, or neutral? The way that works for naive classification, which is why it's really nice to use sklearn's library, is basically it's going to say the probability of it being, you know, let's say neutral, probability of it being so positive, probably being negative, and it's going to test it against everything else. So basically have those three probabilities each. So it's going to do three different basically calculations. This one is technically, there's technically two equations here, right? It's just we replace ham with spam. But the reason why we don't have to do that is because if we know it's not spam, then it must be ham, right? So we just do one minus that probability. Okay, cool. Any questions about conceptually like what we went through or anything like that. How are we feeling? Thumbs up, thumbs down. We don't understand it. Not sideways. Okay. I see a thumbs up. I see a couple of thumbs up. Okay, cool. All right. That kind of helps gauge me about how you're feeling. Like I mentioned, since we have a little bit of time, sklearn, naive Bayes, right here. Like this is what I always like to leave documentation because that's the stuff that you'll probably read a lot of and stuff like this. But you can see here in this case, this is like the actual code, like for an example like this. Now note that this right here is using, you know, numerical values. And if these are our features essentially. This is one data point right here. It's the second data point and so on. And these are the classifications. In this case, there's only two classes, 1 and 2. And we can use, in this case, just like, hey, just import essentially the specific machine learning like algorithm you have. In this case, it's going to be naive Bayes using the Gaussian naive Bayes like actual model. And we can just create that classifier. We can fit it using our knowledge as a supervised learning, so our X and our Y, and then make our predictions, okay? Note that if you instead have like this is kind of like using more numerical data, which you might be more familiar with, like for like the housing prices and like linear regression, stuff like this. If you were doing this for literal document classification, like with natural language processing, you would do something which you guys will learn more about in I think it's module 5, talk about natural language processing. You could do something like a word vectorizer. We're basically saying, okay, how frequently are words actually happening in the document? And this essentially, even though this would be one data point, it'd still be numbers, but those numbers might include just basically the frequency of the words that are happening to that. So you might have like an array that's like literally like, I don't know, 200 like long. It could be even longer than that, like 2,000 or 20,000. And so they think, okay, how frequently does word A, you know, let's say aardvark happen? How often does, you know, the word, you know, apple happen, you know, going down the line essentially. This is where like natural language processing is useful, since it's trying to filter out some of the stuff that's not relevant. But the idea that basically you have this vector that says, hey, how frequently does this happen? And go through there. There's other methods as well that doesn't have to rely on literally the document frequency, but that's kind of like the idea of it, okay? And again, if you just literally said how frequently things happen, like, oh, the word, you know, aardvark occurs 2 times in this document, right? You can have Gaussian naive Bayes actually take care of that. So you don't actually have to do the full process of like what we just went through. Okay, cool. Any questions at all? Cool. So yeah, yeah. So that's kind of it. Naive Bayes, Bayes theorem. I will mention that I know like one part of it that kind of throws off people a lot. MLE from section 26. Quick shows of thumbs. How do we feel about MLE? Great, not so great, like sideways. Yeah, that's the reaction I expected. Yeah. One thing I'll tell you about maximum likelihood estimation, MLE, right? The big thing about it is like people are like, what the heck was going on? When people actually like I think when they read the curriculum, particularly like trying to go through understanding MLE in particular. Note this kind of relates to naive Bayes and just classification in general, is the main idea there is basically saying, what is the thing that's going to maximize the likelihood, right? So basically saying like, what's the likely thing to happen? So basically this whole formula, like you guys, I'm sure you guys have kind of gone through, I'm trying to remember where it was exactly in the curriculum, but when you go through this, they kind of give this long like thing about explaining like how to calculate MLE, and then there's this whole bunch of math. They talk about monotonic functions and stuff like this. The main thing you have to realize is just say, hey, the most likely, the MLE is basically just going to be what's the most likely thing that's going to happen. So, and building it on there. It sounds very scary, but honestly, you don't have to come across it too often, and you don't have to do that formulation every single time. Essentially, that's kind of just an extra part of like understanding the formula itself. But I just wanted to mention about that. It's like, hey, like if you come across MLE again, it's just more about saying like, oh, what's the most frequent thing that's actually going to occur, versus saying like, you know, I think that sometimes when people talk about MLE, it looks very like, it's very math intensive, and it's like, what is going on? And the main thing is saying, oh, we're just looking to see, you know, what is the most likely thing that's going to result in the thing that we see.
So
Yes.
how is that related to Bayes theorem?
Yeah, so we can use Bayes' theorem to figure out what is the most likely thing to happen. And that's essentially what's going on here. So that's why I said like, it's like, oh, like it's good to know, but like know that you don't have to like really like freak out about it in a lot of ways. Like it's like, oh, like how does MLE? It's like, oh, that's essentially what we're doing right here. Cool. All right. Yeah, we have a few more minutes left. Let's see here. What are you guys talking about tomorrow then, or supposed to talk about tomorrow for a study group? Just kind of lead you guys in the next part. Do you guys know? Do you guys have a study group tomorrow? Maybe I'm wrong. Yeah.
We're supposed to. It's either the project kickoff or SVM.
Oh,
Yeah,
okay.
I thought it was support vector machines.
Support vector machines? Cool. Yeah, support vector machines are fun. They can be kind of, they can give people sometimes a hard time, I think, just thinking about it. But yeah, that's good. You guys will have then like another set of, what's it called? Machine learning algorithms you can use. Bayes is relatively simple, which is why people use it. It's relatively quick. Support vector machines, when you guys do your Mod 3 project, know that support vector machines, SVMs, tend to, can take a long time. So just kind of be aware of that if you're doing like grid search and stuff like that, especially. In general, like if you guys talk about like speed and accuracy, one that's really good, like one of my favorites to use is random forest. The random forest is relatively quick and does pretty good results. Naive Bayes would kind of be similar to that, where it's like, oh, it's relatively quick to actually compute. Support vector machines have a lot of like iteration on top, which is why it takes a long time. K-nearest neighbors, just because we're just kind of reviewing stuff. I think we're kind of done with naive Bayes. What's the disadvantage of K-nearest neighbors? Does anyone know? Like beyond the project itself, but like more like for industry, like why might you not want to do K-nearest neighbors? Does anyone know by chance?
It's prone to overfitting.
Prone to overfitting, that's one, yeah. There's another aspect too, even if you get a good model.
I thought it was computationally expensive.
Computationally expensive, yeah. It's gonna have to look at every single point, right? So it's gonna take a long time for it to figure that out, which for relatively small data, it's fine. But if you have very, very large data sets, it's like, hey, it's gotta look at every single data point. The other thing on top of that, it's expensive to store. So in order to know the model, you have to know where, you have to store every location of those previous points. And so the problem is then you have to basically have a very large model. So if you have something that, like, for example, let's say you have on a phone and you have k-nearest neighbors, which could be perfectly good. Maybe you got it so it's not overfitting. You're able to train it. Maybe you took in the resources, so you have a supercomputer and just like push through it and you're able to train it really well. You still have a relatively massive model that you have to say that, well, if they went on their phone, you either send them the information up to the cloud, run it through there because it can be stored up there. Maybe it's like 10 gigabytes large. Or you can try sending 10 gigabytes down to a phone, which is like, ooh, that's not super ideal, right? So just kind of know k-nearest neighbors, like it has its time and place, but just kind of know those trade-offs and stuff. And that's the main thing you want to know for machine learning algorithms, is not just like what's the best one to use in this situation, but more like what are the costs and benefits of each one. K-nearest neighbors is relatively easy to implement, which is nice. And you'll get kind of like straightforward answers, but you then have to, have to store the whole thing. Same thing with random forests, but it's less so because you have many random forests and stuff like, or many forests. You still have to store those, but they're relatively smaller than k-nearest neighbors. I saw someone's mic go off for a second.
I was just going to ask, like, realistically, because, I feel like this keeps coming up in the lessons of like, oh, k-nearest neighbors, like it's better if you don't use it for a data set that's too big. But like, what does that actually mean?
Like what's too big?
Yeah.
Yeah, that's a fun one. It kind of depends a little bit. So in general, it all depends on how many features first, right? Because like each data point, if there's many features, that's a multi-dimensional set. If you have 100 features, that's going to be a big data on itself, right? But I would say in general is that when I think of big data, I think like it's got to be like in my head more than 50,000 data points easily. Like 20,000 in my head is like, oh, that's moderate. That's not anything close. But I would say is that you should kind of be aware that as a data scientist, especially as you guys are practicing now, it's tough to deal with really, really large data, like million plus data points. Even like having 500,000 data points can be relatively tough. And so just kind of know is that when you're practicing these things, they might work fine on your computer, like when you're running stuff like that, but it might not be the best action when you go into industry, right? Because if your data set is only 10,000 points, you can run that. I mean, heck, even for 500,000 or 100,000, what we can do called chunking. You guys know what chunking is for like pandas, stuff like this? So let's see here. I think I can show you real quick for pandas. So chunking basically allows you, instead of like, for example, when you guys load data into your machine, right? So let's say you have 5 gigabytes of data, right? But no one's computer is like this. But let's say your RAM is only 2 gigabytes. The problem is that you guys know what RAM is, right? Like your memory. Yeah. So your RAM basically is the thing that's like short-term memory where it loads it into RAM and then feeds it to the CPU, which is like the brains, right? Well, if you have 5 gigabytes of data and you try to put it onto your RAM that's like 2 gigs and then try to feed it to your CPU, your computer's gonna like have issues. Basically, it's like, I can't handle all of this data and pass it off to my CPU. Okay. And so this is where people are like, oh, this is where big data comes in. Where you can get away, I call it like medium data, is that you can get away with having to deal, like you guys will learn this in the next module, I think, when you guys talk about big data and stuff like this. But you can get away with this by doing distributed computers, where basically you have a little computer doing different tasks and stuff like this, and that way you can distribute that work. But one way you can do it is just literally chunk it. Say, hey, let me just read in part of this data set at a time and feeding it in. And usually you can do that pretty decently without having to worry. So something to look into when you guys like start coming across large data sets. For the record, for your Mod 3 project, you probably don't have to deal with any of that stuff. And that's where, working with James too, like you guys have to, are you guys choosing a data set, right? Like, I know there's some data sets suggested, but you guys also choosing a data set. Make sure you talk with that with your instructor, right? So with James, to just kind of get a quick like go ahead, like, because they might be able to, like, James will likely be able to identify, like, oh, like this looks good, but this large data set, or like, oh, this is actually a lot of features for this data points. For example, if you had 100 features but only 1,000 data points, which 1,000 is already super small, but like you probably have too many features to how many data points you have. It just probably wouldn't be sufficient enough to actually find anything useful. So yeah. Cool. I know we're kind of at time, but do you guys have any other questions or follow up on that? No. I'll just kind of point. I know it's in our documentation.
Do you have any recommended data sets for the Mod 3 project?
Yeah. Pick something you're at least kind of interested in. I think it does help a lot. I would probably say if you're looking for a data set, I think you guys are starting it now, right? So like, when's your project due? Is it next week? Is that right?
I think it's a week from Tuesday or Wednesday, something like that.
Okay, so like sometime next week, right?
Yeah.
Okay, yeah, I wouldn't take my first suggestion is don't take too much time trying to find the perfect data set that you want. So that's kind of like my overall, like, oh, what's a good data set to choose? Choose one that's not gonna basically like, I would say if you haven't chosen one already, take at most 2 days from today to pick it. And then whatever you have, stick with that, right? And make sure you get it approved by instructor, right? But one place I like to look at a lot is Kaggle. Do you guys know Kaggle now for Kaggle datasets? Yes, Kaggle dataset has amazing datasets. And they're like, I don't know if you guys have seen this, is that what's really nice about this is if I pick up like a dataset right here, sometimes people actually have notebooks that talk a little bit about that data set. Now, obviously, don't like copy this and stuff and use that as your thing, but you can use it to kind of get an idea of like what, especially if you hit troubling points and stuff like this. So I always like using Kaggle data sets. If you're all like, I would say not from the Mod 3, but maybe as you get to Mod 4 and into Capstone. Do you guys know the Google dataset search engine? This here, okay. So dataset search, which is just like my favorite thing just to go on and just randomly search. So it's datasetsearch.research.google.com. Literally just put in, like, for example, like, oh, bike data. Oops, data. I don't know what that is. Let's say bike information, right? And you can basically, it searches for different data sets. Kaggle's in there a lot. Know that Kaggle's owned by Google, so there's kind of like that play going through here. But you can also find a lot of government sets. Note that this does not mean the super clean data, right? So be aware of that. I would not suggest doing this for your Mod 3 project. That way you can focus on doing the machine learning algorithm parts. Maybe for Mod 4, but definitely talk with your instructor, right? Like, make sure you say, hey, like, this is my data set. What do you think? Does it seem reasonable? And all that stuff. But I think tabular data should be good. Obviously, you wouldn't be doing any computer vision stuff, any too intensive natural language processing, I would keep that for later because you don't have the full tool set to like really get into natural language processing. I like to say mod 3 is kind of like your time to really practice and test out how different machine learning algorithms work. So sticking with tabular data, I would suggest having at least 10,000 data points. There's some exceptions to that, like 10,000 might not be enough, 10,000 is more than enough. But the main thing is trying to find something that has like rich information, if that makes sense. Cool. All right, and I'm kind of time, but these are good questions. Anything else you guys have any lingering questions or thought about? Pretty good.
Okay. Actually, I was thinking about just when you mentioned number of features. So like, I guess that I feel like I never want to give up any like feature columns. Is that
like drop them, right?
Yeah, because I feel like I'm like losing a potentially like helpful, it's kind of like how outliers was really hard because when we did outliers, it's like hard to give up data points, because I don't want to. I want to like keep everything I can. Would you say that that is like that I should get over that then and like be more selective about features and stuff?
Yeah, there's definitely a struggle there, right? Of saying like, do I keep everything because like there's information here, or like do I get rid of it to make it simpler? And one way I can kind of describe this is that for like, I always try to bring it back to like when you're working in industry, what you're trying to end up doing is that if you can do a model that does a really good job with less features, it means that your model now is more robust against other data sets that you might not have yet. And so if you only need like these 5 features versus these, 25, and someone goes, well, we don't have 25. It's like, well, my model only works with those 25, or like this feature was really important. If you can, and then say, hey, like, well, these features are really easy for us to get. And one thing I'll tell you is like, part of your project, right, is to do like the business case, right? It's like how is this practical for your stakeholders, right? And business could be nonprofits too, but just kind of know like your stakeholders, what they care about. There's a couple projects where I've seen, for example, they say, okay, like this is the data, and they actually knew something about how the data is collected and said, this part of the data, these features are actually really expensive for them to extract out. So they actually made the choice of saying, let me test it. Let me train a model with these features and train a model without these features that are really expensive. And they were able to see like, hey, they were actually about the same performance. In fact, they were able to perform to what they needed and what they decided that was that sufficient value. And that's the kind of stuff that you bring as a data scientist and say, hey, like, how can we like not just get good predictions, but good enough predictions and for it to be versatile and valuable enough for your stakeholders. So I wouldn't say like get rid of that feeling like, oh, like you should like not try to keep all the information or whatever, but I think kind of be selective of like what makes sense. And then also be like, I say like be skeptical of your data sometimes. Like there's some features that like, yeah, it's in there, but like, is it really useful or is it really relevant? Or is it kind of like a red herring for like the machine learning algorithm? For example, for this, like, I'll tell you, like, for example, this is kind of almost an ethics, is that if you have a data set that, I'm trying to think of something on top of my head. Let's say like what kind of car they're driving, right? And you're predicting on, I don't know, how healthy they are, okay? In your data set, it says like what car they're driving, right? And you find that the car is actually a really great predictor for health, right? Does that mean you keep it? I don't know, because that might actually instead codify about how much someone's making in that model. And maybe that's not part of your data set. And it's really a proxy for this other part where you're like, you know what? This doesn't make sense for what we're doing, even if it's a really good predictor, right? So that's the kind of thing that you kind of take a second, like, does this make sense for me to keep this? There's also like with your data set, when you guys do test train splits. So you guys know like your train test splits, right? Like doing that. I wish I could have more time to talk to you guys about this. So a big part of it is that there's actually 3 different sets you consider. It's your train, your validation, and your test set. Do you guys know the difference between those 3? So I see a little bit like, maybe not. Your training set is obviously what you're going to feed the model. Say, hey, how well are you doing? Like, or not how are you doing? So you say, hey, like, learn from this information. Your test set is supposed to be more on the lines of, hey, how well are you actually doing? Let me see, let me give you data that's never seen before and see how well you perform. I kind of think of it like the final test, right? Like if you're a student. And then like the training is kind of like the homework and like the practice stuff that you do to get ready for the final test, okay? But as the teacher, you as the data scientist are training this model, you want to know how well it's doing while it's training, not at the very end, right? Because the problem is if you just train it and then look at the test, like how it results, like, oh, it didn't perform very well. Let me tweak a few things and then train it with the data set again and then test it on the test set. The problem is that you're always going to try to bias it towards overfitting onto the test set, even though you haven't directly had it trained from that. Does that make sense? It's kind of like if you know the students are messing up a certain thing, like on this, like if they could take the final test over and over and over and over again, and let's some magical student that forgets the final test every time they take it, but you as a teacher like, oh, like I should throw this in there so they know about the final test. The problem is like they might do really well in that final test, but like the real test, which I don't know, life or like a secondary, final test, they're going to perform worse on because you've been basically biasing them towards this final test you give. So the solution to this is what we call a holdout test, right? We hold out the test and only look at that at the very end to basically evaluate these models at the very end after they're in the training. So you might have multiple models and then test them against the test set. And then that's kind of like the end of like where you're at. And basically you can think of your test set as kind of like emulating data that it will see in the future. So like if you do this in production in like the real world, you might not have data for like how well things are performing until after you launch the model, right? So you want to simulate that environment where it's like, oh, well, it's never seen this data and I don't know how it's going to perform until it's all done training. So the thing is like, you kind of still want to know like how well it's doing after training because it's always going to do really well in that training part. So we have this validation test or validation set. And this validation set is a thing that you can reiterate over and over. Like you train with the full training set, you see the performance on validation. It never trains out the validation, but sees how it's performing. And so you kind of keep tweaking until your validation gets better and better. And then your final one is your test set. And so the thing is like, let's say, for example, you do your training model, it's 99% actually on the training, which is pretty typical. Validation is like, oh, 80%. And you're like, oh, that's not great. Let me iterate it again, right? And your validation after reiterating on it is like 87%. Like, oh, much better. Change a few things again, add some features in there, take some features out, all that stuff. You get like a 95% accuracy. Like, sweet, like awesome. Like this looks pretty good. Let me go ahead and test it now after I did all this iteration on the testing set. Now I'm kind of like, okay, I think I'm done. I think I got everything I needed to. You put on the testing set, and the testing set likely will be lower than the validation set, which is expected though, because it's never seen this before and you kind of probably been overfitting slightly onto the validation. So it might get like a 90% accuracy. If it's like 60% accuracy, you're like, oh shoot, like either the testing set and the validation set are very different from each other, or you really overfit it by accident essentially on the validation and you really should have stopped earlier on. So that's kind of the idea of this testing, training, and validation sets. Also know that sometimes referred to as a dev set, developing test set. Okay, does that all make sense? I know I'm kind of.
So how would you do that realistically? Would you do a train test split and then a train test split on the split? Like,
Pretty
oh,
much.
okay.
Yeah. And the main idea is that you keep the test set separate. And then I know, let's see, I'm trying to remember where pipelines fit in. Oh, is this the last one? Oh, okay, pipelines. Have you guys learned about pipelines? Okay. Pipelines is where you would use that because then you can process the same information without leakage on your training set and then also on your test set. So the idea there is that you can apply the same processes and then apply onto your test set at the very end. I think I talked to James's other cohort about building pipelines and stuff. Maybe I'll share that video out for you guys too. That might be helpful. I don't know. But yeah, that's a useful thing to do. To be honest, it's a subtle point that sometimes can be skipped a lot. But I like to tell you guys as students, like, hey, this is something you should look out for the future, because there's so many people who go into industry who don't realize that subtle difference and they have really big issues where essentially they think their model's really, really great and they put in production, it's like, oh, your model is complete crap. Like it's not working very well at all. So things to consider. But I wouldn't, to be frank, I wouldn't stress out too much on that for this Mod 3 project. But kind of, I would almost like a sense like if you have like a notebook or like whatever you use, like things like look into train tests validation splits. Like look into that and say data leakage. It's a big thing. Okay. I can share the video I had recorded from another cohort's going through a similar thing that recently. Would you guys like to see that too? I could put on Slack.
I would. We're supposed to go over that as part of,
Oh, good.
like along with SVM tomorrow, but I wouldn't mind extra help.
Cool. Yeah, of course. And I always tell people like the more you can get, right? That's why us instructors are here to help you guys out. So, and then if you guys watch that too, like, or if you guys do want to watch that or have information, you can bring that to, hopefully it's James tomorrow, or whenever you guys talk about this, you can bring that up and say, hey, you know, we had this part, can we go into more detail about this specific thing? Yeah, cool. All right, well, I'm way past time, but hopefully you guys find it useful and everything like that. I'll have this recording, it should be recording right now. I'll have this recording up if you guys want to review parts of it. I'll also make sure to share this repo since we used a few of those things for naive Bayes and stuff like that. So I'll make sure to share that out too on Slack, that way you guys can link to it and everything. Okay. Cool. And if you have questions, feel free to message out too. You know, I know James is out probably out today, but you know, feel free to do the DS support squad. Any instructor, you know, for example, who's like subbing in essentially, feel free to tag us. We're more than happy to help. Okay. All right, everyone. Well, take care. Great meeting you all, and hope to see you guys around more.
Thank you.